Kia ora. We're having a look at page 67 and we're just going to have a look at what kinematics is. So kinematics, as it says here, is the study of motion. Pretty much it's how you can apply what we're learning in calculus over in physics. But because there's so much crossover, it's totally worth learning this stuff for Mat 2. It's also quite cool to have a good understanding of this, even if you're not doing physics. Okay, so for me, the best way for me to get my head around the ideas in kinematics is to pretty much remember this one example is what I do. Right? So what I think of is the Usain Bolt 100-meter sprint, and I use that to remember the three terms. So the first thing that we are going to be looking at is displacement. Now displacement is pretty much distance. It's not like I can't really glance over that, but displacement is fancy distance. It's way smarter. It's not. It's like smart distance, right? It's gonna look exactly the same in this example of Usain Bolt, because Usain Bolt, he is starting at 0 meters, and he's gonna go and sprint over to 100 meters. So actually, his distance that he went is 100 meters. But also his displacement is 100 meters, right? Because it's all we're measuring is from his starting point over to his finishing point. So I've got an image here. I just want to show you what makes displacement better. So the difference between displacement and distance is that it's not very clear to you guys. Right, is that distance is a measure of how far someone has traveled, whereas displacement is actually a vector. It's sort of like as the crow flies from point A to point B, but also if, say, the person ran some distance and then ran back to the start and then ran over there, the displacement is always just a measure of how far from the origin somebody is, right? It can also go backwards, so if the person like ran over here and then ran back and backwards, you could use like a negative number to talk about displacement. It's just a smarter way to think about it, because most of the time we're not so interested in the like bit of a tour that the person went on. We're more interested in how far away from the origin they are, and that's why we are going to be using displacement. Okay, so let's get rid of that and go back to Usain Bolt. Okay, so we're looking at his displacement in blue, and we're going to call that S of t. I know it's a little bit silly. So we're going to go, our first thing is displacement, and it's going to be S of t. Now, how we're going to remember that is we're going to use this S here. Normally, if we were using distance, we would get the D and it would be easier to remember, but the way I remember it is there is this S here, and that's why we do S of t. What the heck does the T mean? T is just time, right? And it's usually, and this is going to be confusing, it's usually measured in seconds, but this S is for displacement, right? This is displacement in regard to time, and time will be measured in seconds. Don't get confused by that. Okay, the next thing we are going to look at will be velocity. Now, velocity is the fancy way to talk about speed. Pretty much, just imagine we were trying to make it as confusing as possible for you in terms of selecting letters and words, and yeah, that's how we do kinematics. So velocity is the new fancy way of talking about speed. Okay, so we're going to measure velocity, but don't worry, you get a V for velocity, so you can remember that one. That's going to be in V of t. It's how fast you're running at what point in time. Okay, and the next thing we've got here is acceleration. So acceleration, don't worry, you get an A for this as well. So acceleration is going to be A of t. So these are the things in kinematics that we're having a look at. Now, what I want you to see here and sort of recognize is that Usain Bolt starts off and his displacement or his distance from the origin is 0 at the start, and this is normally the case in kinematics, right? So he starts off here, he covers this much ground, and this is measuring. So see, on the x-axis we have time. It's sort of going off the screen a little bit. That t is time, and it's in seconds, right? This is, he starts off, and as time increases, his displacement increases from 0 meters up to 100 meters. So he runs and he covers a lot of ground, and he gets to 20 meters in, say, what? Oh, actually we can click on this and look. He gets to 20 meters at about 2.5 seconds. He gets to 40 meters in about 4.5 seconds. He gets to 60 meters in just under 6 seconds. And he gets to 80 meters in 7.5 seconds. And then he gets to 100 meters at whatever his amazing time was. I think I've edited this slightly, but it's pretty accurate to what he actually ran. Okay, so this is his displacement. It is his distance in this case as well, right? It's how far he is running over time. Now, displacement is related to his velocity, right? He starts off running at what speed? He starts off running at 0 meters per second, but his velocity increases. He runs faster and faster, and by about, oh no, I want to follow the velocity curve. By 3 seconds in, he is running at about 11 meters per second, and he peaks out, and his velocity doesn't increase too much, and his velocity starts decreasing here. So he runs slower and slower until he crosses over the finish line. So he gets to his max speed, he increases very slowly after that, and then he planes off just before he finishes the race. So that's velocity. Velocity is speed. Okay? Now, velocity is related to his acceleration. How fast he is running is based on how fast he accelerates. So the idea of acceleration, I think you can think about it pretty easily when you're driving a car or something. It's when you plant your foot on the gas, and it's how fast your speed is increasing, right? So it's actually interesting that because he jumps off those starting blocks, his acceleration is instantaneously really high. So he's instantly picking up speed like really fast, and his fastest acceleration is right at the moment go, right off those starting blocks. His acceleration is really high, and he is increasing in velocity, but his acceleration is actually decreasing. He's not decelerating until here, but his acceleration is decreasing because it's so high at the start. As long as his acceleration is above 0, his velocity is increasing. And then there's a point where he hits max velocity and he actually starts to decelerate or slow down up until this point. Now, the interesting thing about kinematics is that these three things are related to each other. Your distance or your displacement is affected by your velocity, right? And your velocity is related to your acceleration. So these things are related to each other, and actually they are related to each other through differentiation. What is differentiation? Differentiation measures change. So of course your displacement is measured by how much your velocity is, how high your velocity is. The change in your displacement is velocity, and the change in your velocity is acceleration. So if you differentiate displacement, you're going to get to velocity. And if you differentiate if you differentiate velocity, you're going to get to acceleration. So these things are all related. And we could also think about it in terms of anti-differentiation. From acceleration, if we anti-differentiate acceleration, we are going to get to our velocity. And if we anti-differentiate our velocity, we are going to get to our displacement. So these three are related through differentiation and anti-differentiation. We can jump between them. So let's go back to our example and have a look at that. So that's all happening here in the top left. See how we've got S of t, that's our displacement, and it's being modeled here by a negative quintic. This blue thing is a negative quintic. And you can see, I've tried to make it as clear as possible, that when you differentiate, you get from here down to here. Differentiate here down to here, here down to here. It's just polynomial differentiation. So displacement differentiated would get us to velocity. And then if we got our velocity and we differentiated it, we would get to our acceleration. And let's do it in reverse. Acceleration, if we anti-differentiated this, it would take us up to velocity. But wait a second, wouldn't we have a plus c here? Ooh, we would. We would have a plus c. But the thing about this plus c is your velocity at time 0. How fast is Usain Bolt running at time 0? He is running at 0 meters per second. So actually, when t is 0, 0, 0, the c is going to end up becoming 0. And most of the time, that will be the case, that your velocity at time 0 will be 0. So this plus c will get taken away. The other thing is when we anti-differentiate velocity and get to displacement, we'd also get that plus c, but it's going to be a different one, so I'm going to put plus k today. Right? But what is his displacement at time 0? Usain Bolt starts the race having covered no ground. So this would also become plus 0. And that happens most of the time in kinematics as well. So these relationships, I remember how they're related by going back to Usain Bolt most of the time. And it keeps me realizing that if I differentiate displacement, it will take me to velocity. If I differentiate velocity, it will take me to acceleration. If I anti-differentiate acceleration, I get to velocity and then back to displacement with anti-differentiation. And these constants of integration most of the time end up becoming 0 in kinematics, but that's not always true. It's just most of the time, and it's probably a solid assumption to go by as well. Another thing is the model starts off with its most complicated model, and it goes down to being less and less complicated. So you can build up a scenario by knowing acceleration. All you need to know is the acceleration, and then you can just go and anti-differentiate, and you can build a more and more complicated model up to displacement. And usually it's just you're just going to get given a point or know the fact that the initial velocity is 0 or the initial displacement is 0. And essentially that is kinematics at level 2.